Half-micron wavelength of optical light limits the resolution of an optical microscope. So to overcome this, in the 1930s, Ernst Ruska proposed a microscope in which electrons were accelerated from a small source towards a phosphorescent screen, so that an object placed in the path of the source close to it would cast a magnified shadow image, the magnification of which could be arbitrarily large because electrons are particles. Ruska was mortified to hear about quantum mechanics and discover that after all his precious electrons might be waves, but in fact the wavelength associated with the probability amplitude is very small and not a problem. I begin with the scanning electron microscope because this is the single most useful piece of apparatus available to the nanoscientist. So up here is a source of electrons, field emission or thermionic gun, typically held at a very large negative potential with respect to ground, and the sample itself is grounded. These condenser lenses here collect the electron flux from the source and bring it to an objective here which focuses it to a very fine point. The electron beam is deflected on the sample by magnetic coils here showing X and Y deflection and scanned over the surface, much as is the case in a scanning probe microscope, except now it's a very fine pencil beam of electrons being scanned quickly over the surface. Typically, the images are formed by collecting the secondary electrons that are knocked out of this sample by the high-energy electron beam when it hits it. However, by energy filtering and collecting just the backscattered electrons, another type of image can be formed. By collecting the transmitted electrons, a scanning transmission electron microscope image can be formed. By collecting light from semiconductor samples excited by the electrons, a cathodoluminescence image can be formed. And finally, by collecting X-rays generated by the interaction of the electrons with the elements in the sample, an X-ray image can be collected, and indeed elemental analysis done through the wavelengths of the X-rays characteristics of excitations of the inner shells of elements. Here is a picture of a modern scanning electron microscope, and a sort of characteristic image which demonstrates the capabilities of the SEM. It's an image of a fly's eye. So the wonderful thing about SEMs is that they have enormous depth of focus, can take images very rapidly. Remember, in a scanning probe microscope, you must remain in contact with the surface. Here one can scan an image a long way of great topography. However, the imaging is done in vacuum, and a dried fly's eye is a good insulator. So in order to stop it charging up and deflecting the incident electrons, it's necessary to coat it with a metal. This fly's eye has been coated with gold. It's possible to get a resolution that approaches a few nanometers from a scanning electron microscope. What about this source of electrons? The most common source of electrons is a thermionic emission gun. The idea here is simply to raise the temperature of the source so that here is the Fermi energy, and here are free electrons, and this is the work function. The idea is to make the temperature of the source large enough that this factor, e to the minus work function over kT, results in some non-trivial number of electrons being freed by the heating of the sample. This requires a very hot incandescent sample, many thousands of degrees Kelvin, and this means that the energy distribution of electrons in thermal equilibrium with that electrode is, of course, very broad. We discussed the Maxwell-Boltzmann distribution in Chapter 3. The problem with a broad energy distribution is that all of the energy filtering techniques required to form images and the focusing itself, which suffers from chromatic aberrations because the focusing depends on the electron energy, all become complicated and resolution reduced. A way of getting very monochromatic electrons is called field emission. This is a beautiful problem in one-dimensional quantum mechanics. And so the idea here, drawing once again this potential barrier, where here is the Fermi energy where the available electrons sit, and here is the work function, and here the free electrons. If one places an electric field on, which is equivalent to a potential gradient, then here is the potential gradient. One forms a narrow barrier through which electrons can tunnel to become free. The problem is a really neat one in tunneling theory. The result is put down here. I would urge folks who are interested to look at the solution. It's cute. Let me just say that the electric field can be made very high by making the radius of curvature of the field emission gun very small. So down below is the expression for the electric field owing to a charged sphere. And it's re-expressed in terms of voltage and the diameter or the radius of the sphere, and the result turns out to be very simple. So if one has a sphere of radius A and one applies a potential V with respect to some distant ground electrode, then the electric field is just given by V over A. So if the radius is on the order of nanometer and one has tens of volts, very large fields on the order of volts per angstrom can be applied. These are comparable to the electric fields in atoms, and that is how field emission occurs. So how do you focus this electron beam? The formula on the top here is Newton's second law for charged particles. The force on the particle is just the charge times the electric field E. The magnetic force is given by the Lorentz equation, the velocity of the particle cross product with the magnetic field. Now this means that if the particle has a velocity vector in this direction, the field in this direction, the force will act perpendicularly. So if there is an electric field downwards like this, then the electrons will be accelerated in this direction, but they will spiral. If there is also a B field this way, they will spiral around the B field like this. The result is that by setting up the geometry appropriately, one can make the electrons spiral to a point that can be quite small. Electron wavelengths, as I alluded to, are actually very tiny at any sensible accelerating potential. Here is a formula. It's simply the de Broglie formula, where I've used the square root of the kinetic energy of the electrons as the momentum and expressed the energy in terms of the voltage V0 that is applied. And you can see at 5 kilovolts it's on the order of 0.2 angstroms. This formula needs to be corrected for relativistic effects if the energy of the electrons approaches 100 kilovolts or so. 511 keV is the rest mass of the electron. And here is a way to fix up V0, correct it for relativistic effects at high accelerating potentials. How does one get really high resolution? The answer is to use a transmission electron microscope. So in a transmission electron microscope, a source of electrons is focused down to a pretty small point on a sample and then refocused again onto an imaging device down here. Now, if the sample wasn't in place, one would merely form an image of the source up here, down here. But what happens in the sample is electrons are diffracted by Bragg reflection of crystal planes, for example. So in fact, it turns out that almost any sample will give fringes of atomic dimensions owing to the collection of these diffracted beams and their imaging on the plate down here. However, this is not genuine atomic resolution. The problem is this: when the sample is very thin, as it needs to be for this technique to work, the contrast exactly at focus is close to zero. Atomic fringes occur when you defocus the microscope so as to in effect just carry out a diffraction experiment. My colleague John Cowley many years ago found out a way to work out a perfect compromise so that the sample was just slightly out of focus enough to increase the phase contrast of the diffracted beams, but not so out of focus that atomic resolution was lost. And using this technique now, individual atoms and defects in crystals can be imaged routinely. The image here shows a multi-walled carbon nanotube on the left, and on the right one has zoomed in to see the multiple rows of carbon atoms in the sample. With aberration-corrected microscopes today, the imaging resolution is a very small fraction of an angstrom.